Okay, here we're going to go over the conservation of momentum. First thing we want to do is find out where the conservation of momentum comes from. And it is largely a consequence of Newton's third law. Here what we're going to do is consider two objects that will be interacting with each other. And while they do so, they'll exert forces. And those forces will in fact constitute an action-reaction pair because there's two objects pushing and pulling on each other. And this is the force that object 2 exerts on object 1, and this is the force that object 1 exerts on object 2. That means they'll be equal in magnitude and opposite in direction. In addition, while these two objects exert forces on each other, they'll be doing so for the exact same amount of time. For however long object 2 pushes on object 1 will push on object 2. So the times of interactions will be exactly the same. That means when I multiply the forces by the times to get the impulses must be equal and opposite. So the impulse that object 1 exerts on object 2 will equal the impulse that object 2 exerts on object 1. So these must be equal and opposite. But the impulses will equal the changes in momentum, which means the change in momentum of object 1 must be equal and opposite to the change in momentum of object 2. Or another way of putting that, the momentum gained by one object must be exactly equal to the momentum lost by the other object, meaning the total amount of momentum should stay the same. You can see that by simply taking this equation right here, which you just derived from Newton's third law, and saying the change in momentum is just the final minus the initial for both objects 1 and 2, and then taking and rearranging the terms so we put all of the initial momentums on one side of the equation and all the final momentums on the other side of the equation. Then we end up with the initial momentum added up right here must equal the final momentum, or momentum is a conserved quantity. It stays constant because the initial amount of momentum that we have is the final amount of momentum that we have. Note we're saying here that the vectors have to be equal. For the vectors to be equal, both the magnitudes and directions must be the same. So what we have just shown is that the conservation of momentum is a consequence of Newton's third law. I will use the acronym CoP as a shorthand when I mean conservation of momentum. And the P simply comes from momentum symbol is P. Now let's consider some examples. The first example I want to consider is one you've already done in freshman physics. So this should be very straightforward. Here we just have two freight cars. They're on the same track, and they're going to be moving towards each other. They will collide and basically become coupled together. I want to find their final velocity, and it'll only be one because they'll be stuck together. Now here we want to consider there's a system, and the total momentum of this system will stay the same. That system must be isolated, and it must be closed for the momentum to be constant. Our system will consist of the two freight cars. It'll be closed because there'll be no mass coming in or out of the system. That's what we mean by closed. It will also be an isolated system in that there'll be no net external impulses applied. There will be gravity pulling down and the normal force pushing up on both of the cars, but they'll be equal and opposite. Therefore, no net external momentums will be applied, so the momentum should stay the same. So what we need to do is simply find the initial momentum before the collision, which we just take the masses and the velocities, multiply them together, and add everything up. And we find that there are 750 kilogram meters per second of momentum before the collision. After the collision, the two masses are coupled together, so we'll add them together. They'll have a common final velocity. And that must equal the initial momentum. So we take and plug the numbers in, and we find out that their final velocity combined must be 0.3 meters per second. And since it's positive, it means they're moving to the right. Our next example will be a little more involved. Here we'll have a cannon, which is at rest. It will be firing a cannonball horizontally with a mass of little m and a velocity v. And the velocity v will be measured relative to the cannon. What we want to do is find the recoil velocity of the cannon, but that we'll want to do relative to the ground. Here our system will consist of the cannon and the ball. It will be closed. We'll also treat it as isolated because although there will be a vertical force, namely gravity will be pulling the cannonball down, but that will mean that the y component of the momentum will not be conserved. We're only going to worry about the horizontal or x component, and there are no external forces acting in the x direction, only in the y direction. One thing that makes this problem a little bit different is we have to here be careful of our frame of reference. We're going to measure the momentum before and afterwards relative to the ground. However, the velocity we are given is relative to the cannon. So we need to use our relative velocity relation. So the velocity of the ball relative to the ground, which is what we want, that's this VE right here, because we're going to measure momentum relative to the ground, equals the velocity of the cannonball relative to the cannon, that's what we're given, plus the velocity of the cannon relative to the ground, that's what we want to find, that recoil velocity of the cannon. Now we can use is momentum conservation. We have no momentum to start out with, therefore we must have no momentum to end up with. But the final momentum must equal the mass of the cannonball times its velocity relative to the ground, plus the mass of the cannon times its recoil velocity relative to the ground. Then we can plug everything in and solve for the recoil velocity of the cannon. And note the sign we end up with is negative, which simply means the recoil is in fact backwards. Now the last example I want to consider is what's called a ballistic pendulum. And this you want to be careful with because this is a problem that effectively anyone taking this kind of a course should be familiar with. You should understand what a ballistic pendulum is and how to use it. There are various forms of the ballistic pendulum. Here we're going to use a pendulum form. We also could take this block right here, rather than attach it to a string and make it a pendulum, we could attach it to a spring and have it compress a spring after it gets hit by this bullet. Or we could put it on the edge of a table and let the block fly off the table and land on the floor. But in any event, it always comes with a small mass moving at a high velocity, hitting a heavy mass that is initially at rest. And we have always set it up so some way we can calculate what the final velocity of the block is after the collision. Here we're going to use a pendulum, so we'll measure the angle that it swings back at, this angle theta right here. And we're going to use that to back out how fast the bullet had to have been going before it hit the ballistic pendulum. Our first step is to use the conservation of energy in the pendulum part itself. We've already used the conservation of energy in a pendulum, and we're going to use that again here. So at the very end right here, when it's at the angle theta, its velocity is 0, so there's no kinetic. All the energy is potential. And this energy will simply be mg times h, and h will just be the height above its starting point, and that height will simply be this length L minus L cosine theta is the height it goes up. And that tells me that 1/2 times the total mass times the velocity coming out of the collision squared equals the potential energy. We solve that for the velocity v. That tells me basically the velocity coming out of the collision. I know how much mass was involved, so that I know how much momentum came out of the collision. That must equal the amount of momentum that came into the collision, and that all came from the bullet. So the bullet's initial momentum must equal the block's final momentum, and that we know. We can then back out how fast the bullet had to be going. Now what I want you to do is answer a few questions on the attached Google Sheet.